point out something that I've been working on a little bit within the last year. You know, it's kind of tough. You get here and you have to present something new. Every year for 25 years, I tell you, it's 25 different things you have to come up with.
Too young.
Okay, so only 25, but I don't know how long this workshop is going on, I think. Okay, anyway, so I came up with something new, just in case, and actually it turns out it's related to a lot of talks we have already heard, so in that sense it's quite nice. I don't have to introduce much, and I can go right away to what I have been doing. It's about the dwarf spheroidal galaxies, and you all know that these galaxies are quite funny in the sense that they have masses similar to a globular cluster, 10 to the 5, 10 to the 6 solar masses, but their radii are much larger than a globular. A globular has maybe a radius of 50 to 100 parsecs. Dwarf spheroidal has a radius of a kiloparsec. So in that sense, its mean density is a factor 1,000 smaller than a globular cluster. Yet, like globulars, the dwarf spheroidals are part of the halo of a galaxy, of the Milky Way and Andromeda, and therefore they probably trace the accretion history of the Milky Way, which is in itself quite interesting. We learned a lot about how filamentary accretion happened, maybe because dwarf spheroidals seem to be in large disks or circles or whatever that means, but they are also fascinating by themselves. And one of the most fascinating properties certainly is they are very diffuse, so they should be subject to very strong tidal interaction with the Milky Way. And then you learn something about the dark halo and all of these tidal interactions and their internal structure. And this turns out to be problematic. First of all, there is strong evidence for tidal interaction. If you look at the famous Sagittarius dwarf spheroidal, and we had a talk about this already, then we clearly see that this is now being tidally destroyed. And there also seem to be extra-tidal stars. That's what they are called, but also I will tell you they can't be extra-tidal, seen in almost all dwarf spheroidals right now. Okay, so there is tidal interaction. Now, the fascinating property which the dwarf spheroidals have is their velocity dispersion. This is the stellar velocity dispersion of the dwarf spheroidal. And this is of order 6 to 10 kilometers a second, which I find absolutely puzzling. First of all, if you look at the extended property of these systems, if they would be in real equilibrium by themselves without dark matter, the velocity dispersion would be 1/10 of a kilometer per second. So that clearly indicates that they are kind of confined by something else. But this 6 to 10 is characteristic for a for a standard turbulent Milky Way type disk. Below in the ISM in the Milky Way, we have 6 to 10 kilometers a second. And it always seems to be so when you have star formation in present-day disk galaxies, not at high-redshift disks, but present-day disks, you get this. So this seems to be the condition in the ISM when these stars formed. But these stars are not self-gravitating anymore. Everything was puffed up or whatever. So why should the stellar population still remember the velocity dispersion of the ISM inside which it was forming? So this is for me absolutely confusing. If you look at the disruption picture by Avishai and so on, where you say, okay, you form first a stellar system, then you blow everything out, the stellar system expands. You know what expansion means? Expansion always means cooling. It happens for the gas, it happens for the stars. The dispersion should become much smaller than the dispersion when they were self-gravitating in a dense disk. So it's a big puzzle. Another problem with this dispersion is it's constant. If you look at one of Carina, for example, it's constant all the way out to the one to KPC. The stars that are further out, if they came from the inner region, they should have much less kinetic energy than the stars in the inner region. So how can the dispersion remain constant? What made the system isothermal in the first place? Well, okay, this is one of the puzzles. And in order to solve the puzzles, we need to look at the component that confines these dwarf spheroidals. And that obviously seems to be dark matter. And there's this kind of fascinating observation by Strigari et al., where they see that within a radius of 300 parsecs, if you measure the kinetic energy and the dynamical mass, you always find 10 to the 7 solar masses. That means these dwarf spheroidals inside 300 parsecs have always in the 7 solar masses of dark matter. Now for me, this is not anymore a mystery. Because if the velocity dispersion is constant, you multiply it with 300 parsec, you divide by g, you get the dynamic mass. And it must be 10 to 7, it can't be anything else. It just simply means that all toroidals have the same velocity dispersion, which is equal to this gas disk maybe. But why? Yeah? Not anymore true? So what do you...
Velocity dispersion is different in those little things.
So it's not anymore 10, but then how can you get this mass?
Because they have different half-life radii.
No, but I put it within 300 parsec.
No, but you can't use that. You can only use that equation at the half-life radius.
Yeah, but this is within 300 parsec.
Yeah,
then this equation is...
The little things is smaller than 300.
I don't care. You know, if they say, if this says at 300 parsec, then they say the mass within 300 parsec, then this equation applies, independent of what the half-life radius is, you know.
Yeah, it's dependent on velocity and
So you say the dispersion within the half-life radius is different. No, wait, no. Then it doesn't work. Then I can't get this mass. I mean, look, if I take a velocity dispersion of 1 kilometers a second, multiplied with this over this, and within 300 parsecs, I'm not...
written down is not true for all velocity anisotropies.
Anisotropy, okay. You didn't mention this word. Anisotropy, okay, is something else. But this, okay, I'm running out of time already. This always happens. I don't know why. Usually it's Joe or Avishai, but they didn't say anything yet. Oh, already starting. Okay, so don't disturb me. Okay, anyway, I think it's quite interesting with respect to Sandy's and Joel's talk. These objects are elongated. They are prolate, maybe. And they might be those objects which you have seen at high redshift. They might have been dark matter dominated from the very beginning, but somehow could form stars anyway. And so this dispersion and whatever this all means might then be connected to how these strange objects formed. And so in that sense it might be interesting to study them more. But actually I wanted to do something else. I wanted to go and look at the dark matter structure in greater details, because once we understand that, we can understand how the stars might have formed inside. It might also be something you can compare with your numerical simulations of the dark matter structure. Well, the problem is you can't see dark matter, so you have to take a tracer population, the stars. And there has been this knowledge floating around, as usual, if knowledge floats around, nobody knows why, that the dwarf spheroidals have exponential profiles. And you see this here, the Sérsic index, as you all know, and the dwarf spheroidals are in this regime where n is of order 1. And then came this very interesting paper by Corman and Freeman, where they said, no, it's actually wrong. When I saw this, it was kind of like an eye-opener. Look at Carina. Carina, you look at the logarithm of the velocity, the surface density, but it's not plotted versus r, it's plotted versus r squared. And you see it's a perfect linear relationship. So they say sigma does go with e to the minus r. It's actually a Gaussian distribution that these objects have. Once you have this, and this is the scale length of this Gaussian distribution A. Once you have a surface density which is Gaussian, you can show the density distribution also have to be Gaussian with the same scale length. So you already immediately get the density distribution of the stars and their scale lengths. And we know that these objects are isothermal. So you can use hydrostatic equation and determine which mass you need to get the Gaussian distribution. And it turns out, if you assume that the mass goes as r to the third power, that means you have a constant density of the underlying mass distribution, then you perfectly can reproduce this Gaussian distribution. So what they basically show is that the stars trace a region where the mean dark matter density, has to be constant. And that I found quite interesting. And you can actually get the dark matter density from the scalings. Well, so it seems to be the following. This is the dark matter distribution which you have. It's not like this. And actually, inside this region, the velocity dispersion of the dark matter has to become constant. It can't decrease, as usually assumed in cosmological simulations. And according to NFW, I can't show you now why it has to be constant. You just see it from integrating this analytically. And so actually these dwarf spheroidals trace an isothermal constant density dark matter core. And it would be interesting to see what you find in your, maybe this is if you have radial inflow and along filaments you generate something like that. I don't really know. And okay, so we can get the dark matter density from the scalings. But I also want to know the size of the core and the mass of the core, because it tells me something of where the stars can be distributed and the origin of these cores. And the problem is from the simple analysis which we said here, we can't get it. So we need more information. So that's where I came in and I wrote a little paper about that. It turns out actually the dark matter density can't be exactly constant. Because if it is constant, the left side of the hydrostatic equation is 0, and then the mass must be 0. You always need a pressure gradient to compensate gravity. So you need a density gradient. And you might say the density gradient of dark matter, who cares? But it turns out to be dominant. Without the density gradient, you can't explain the stars, as I want to show you. So we have to do it a little more sophisticated. And so what I first did, I just integrated this isothermal equation for the dark matter, assuming that we are looking in regions where sigma dark matter is constant. Then I find this kind of profile. You see you get indeed a roughly constant density core, and then you turn down at some point. This is the logarithmic density slope. It is 0 in the inner region. Rho is constant. Then you get a decrease. Actually, it overshoots, goes deeper than r to the minus 2, and then it approaches r to the minus 2 from below. And that's the typical isothermal sphere which you have, a finite isothermal sphere. And you see, the point where it turns down, this core radius, depends on the velocity dispersion of dark matter, which I yet do not know, and it depends on the central density of dark matter, which I know from the scale of the stars. But I want to get also the velocity dispersion of dark matter. So the question is, how do I get it? Well, it turns out you can use the stars to get it. Look, the stars fulfill this equation, the dark matter fulfills this equation. Both sit in the same potential. So actually, I can remove this part. I do not at all need it. I can take this one, and you see the solution is trivial. The stellar density distribution is the dark matter density distribution to the power of kappa, where kappa is just a ratio of the velocity dispersion square, temperature square. So if I know the stellar density distribution, immediately I have the dark matter distribution if I know the ratio of the temperatures between dark matter and stars. It's also quite interesting because usually if it's an isothermal distribution, you would say this goes to infinity. The mass diverges. But you see the logarithmic slope of the stars is kappa times the logarithmic slope of dark matter. If this goes to -1, -2, and kappa is of order 5 or 6, then you see the logarithmic slope of the stars is very, very steep, despite the fact that they are always isothermal. But there's a finite edge, which you would look like a tidal radius or call like a tidal radius, but it's not. It's just simply confined by the core of the dark matter. That's what it is. Anyway, so what we then can do is we then place a stellar system into my dark matter core with certain kappa values, and I look at how the system looks like. And indeed, this is the surface density distribution of the stars. You see the surface distribution, if you plot sigma versus r square, and sigma over r versus r square, roughly in the inner region, is Gaussian, but not completely. But the slope of the Gaussian depends on the kappa, which is important because it gives me an information about kappa. First of all, I can check if I look at the scalings of this rough Gaussian, whether it fulfills roughly the relationship which we had for precisely constant dark matter density core. And indeed, it turns out it does so. We can then work out the dark matter density again from the scalings, and we have a correction factor. The correction factor is 1 if kappa is very large, but the correction factor actually goes above 1 when kappa becomes of order 1. So we need still this kind of temperature ratio. The question is, how do we get this temperature ratio? Well, it turns out we haven't yet used the steepness of this inner slope. And I told you the steepness of this inner slope, which is the scalings of the stellar distribution divided by the core radius, depends on kappa. That's already said. So we get this kind of equation just from the analysis of this two-phase model. And okay, so then we have this. Well, another thing I have not used is going farther out. And all the dwarf spheroidals seem to have cutoff radii. They have a tidal radius, which is given by the size of the core radius of the dark matter, and they have a core radius themselves, which is basically where the density distribution becomes flat. And you can place King profiles through them, and you can determine the King concentration of a dwarf spheroidal galaxy. And it turns out you can do this for Kreiner, and you can do this for Sculptor, for example, and you find different concentrations. The interesting thing is, these concentrations, if I now use my models, which I can place through this observation, correspond to models with different kappas. So if I measure my concentration, that's shown here, I can precisely determine the temperature ratio of the dark matter and the stars. And I have my kappa. So now I looked at the literature, and unfortunately there are only, I think, 8 dwarf spheroidals in the Milky Way, or 6, where the King concentration has been measured. Could be done for more, could be done also for Andromeda. I hope this is being done. So I can determine the temperature ratio of dark matter to stars. And once I have this temperature ratio, the kappa, I can determine the core dark matter density, and I can determine the core mass, and I get everything. So for these 8 galaxies, I've been doing this, and this is the result. 1, 2, 4, 6, 8, yeah, okay, fits. Okay, so this, what you see here, and you were interrupting, so I get another minute. Well, he's already silent. He knows me. He knows me. You can sit down again. I mean, it takes some time. Okay, so here, these triangles show the stellar velocity dispersion versus the Gaussian slope or scalings of the stars. And they lie at about 8 kilometers per second and so on. Here you see the dispersion of the dark matter component and the core radius of the dark matter component. And the interesting result is that the core radius of the dark matter component is twice the scale length of the stars. So the scale length of the stars is indeed tracing the core of the dark matter halo, and it seems to be quite robust. That means if you just measure the scale length of the stars, you know the core radius of the dark matter. In addition, the dark matter's random motion velocity dispersion is 1.5, 1.6 times the velocity dispersion of the stars. So somehow the stars have been heated in this extension process to roughly the dark matter random motion, but not completely. And I have no idea why it is 1.5. Why not 2.6 or 1.3 or 10? Why is it 1.5, 1.6? There's something, it's a prediction and something which has to be tested by whatever model we have. Another interesting thing is now looking at the density in the center of the dark matter, the core density versus the core radius. This is now only dark matter. We forget about the stars. These are massive galaxies where the core density and the core radius has been measured directly from rotation curves. These are the dwarf spheroidals. And you see they follow the same universal scaling law. The scaling law says that the core density of dark matter times the core radius is a universal constant, always 75 solar mass per square parsec. It's this kind of line. And the dwarf spheroidals follow the same thing, despite the fact that their formation history is completely different. Now, these are not disks, and they didn't accrete much. They have been subject to tides or whatever. And still they follow the same, remarkably, the same relationship at all these massive galaxies. Not only that, as the core radius of these dwarf spheroidals is so small, the core densities of dark matter must be very, very high. So I argue that these dwarf spheroidals are the highest density dark matter regions in the universe. You can't, if you really want to go to high dark matter densities, look at the dwarf spheroidals. And the smaller the dwarf spheroidal, the larger, if this correlation holds, must be its core density, which is amazing. You can do the same for the core mass versus core radius to find a nice relationship too, and you can do it for the velocity and core radius. They follow all the other things. But the most puzzling aspect of all of that is this line. You know, a system is being tightly disrupted if its mean density, I'm done. Anyway, this line is the last one. Forget about it. If its mean density becomes smaller than the mean density of the galaxy inside which it orbits. The mean density of the Milky Way is given here at that radii. And you see, its orders of magnitude smaller than the mean density of the core inside which these stars are bound. So these dwarf spheroidals cannot at all be tidally affected. They would have to move through the very center of the galaxy to really be tidally affected. Sagittarius shouldn't exist. Well, it should exist, but it should not be tidally affected. Because if it sits up here, the tides can't do anything to them. So these extratidal stars are a mystery to me. Okay, that's it. Thank you very much for giving me a little bit of time.
Free in SID. Get it free. It comes right out.
Okay.
Ratio at the center is ratio of dark matter to baryonic stellar matter, roughly.
This is 1,000 or so. It's varying, you know. This,
well, no, but just take an average of your
yeah, so it's about it's a 10 to 8, it's 10 to 7 for dark matter. It's 10 to 5 for the stars. 10 to 4 for the 100 to 1,000. Yeah.
And so, assuming you made the assumption that the velocity is isotropic, is there evidence for that?
The interesting thing is, if it is anisotropic, then it must combine in such a way that you don't see any radial dependence, which is already a little funny because it looks constant in projected velocity dispersion all the way from the center to the outer parts. There is evidence, because we see that these dwarf spheroidals are elongated. They are prolate shape. And there's no rotation. So if they are real, that means when they're not oblate, they're probably prolate. And if they're prolate, there must be anisotropy.
That requires some link. If there was
Yeah.
some anisotropy,
Yes.
your conclusion changed.
Yes, it's a good question, and I've been thinking about that, and that will be the second paper, of course, to go into this. Probably it's not that much. Maybe it's a factor 2 to 1, the excess ratio. So, but it has to be taken into account. But you know all the nasty things. You don't really know the radial distribution. Of course, you know the velocity turn has to be constant with radius, so that helps maybe. And then one can work out and estimate what the effect would be. I think it would change these radii and everything by a factor 1.4 or so, but not by orders of magnitude.
Okay, thanks very much.
Thank you. I think we learned a lot about how filamentary accretion happened, maybe because dwarf spheroidals seem to be in large disks or circles or whatever that means. But they are also fascinating by themselves. And one of the most fascinating properties certainly is they are very diffuse, so they should be subject to very strong tidal interaction with the Milky Way. And then you learn something about the dark halo and all of point out something that I've been working on a little bit within the last year. It's this kind of tough. You get here and you have to present something new. Every year for 25 years, I tell you, there are 25 different things you have to come up with.
too young.
Okay, so only 25. But I don't know how long this workshop is going on, I think. Okay, anyway, so I came up with something new just in case. Actually, it turns out it's related to a lot of talks we have already heard. So in that sense, it's quite nice. I don't have to introduce much, and I can go right away to what I have been doing. It's about the dwarf spheroidal galaxies, and you all know that these galaxies are quite funny in the sense that they have masses similar to a globular cluster, 10 to the 5 to the 6 solar masses, but their radii are much larger than a globular. A globular has maybe a radius of 50 to 100 parsecs. Dwarf spheroidal has a radius of a kiloparsec. So in that sense, its mean density is a factor 1,000 smaller than a globular cluster. Yet, like globulars, the dwarf spheroidals are part of the halo of a galaxy, of the Milky Way and Andromeda, and therefore they probably trace the accretion history of the Milky Way, which is in itself quite interesting, these tidal interactions and their internal structure. And this turns out to be problematic. First of all, there is strong evidence for tidal interaction. If you look at the famous Sagittarius dwarf spheroidal, and we had a talk about this already, then we clearly see that this is now being tidally destroyed. And there also seem to be extra-tidal stars. That's what they are called, but also I will tell you they can't be extra-tidal, seen in almost